I'm going to go over the question 2 from the 2018 AP Chemistry FRQ exam. So the first part here, this whole question is talking about oxides of nitrogen, and it's really a little confusing because, there are several different parts to the question that are not necessarily related. They're just all about oxides of nitrogen. So sometimes students have a little bit of a confusion because they think one part really relates to the other, and sometimes they do, and this time they don't. They're really separate little questions. But a student investigates the reactions of nitrogen oxides. One of the reactions in the investigation requires an equimolar mixture of NO and NO2. And then, be sure to go over what equimolar means. We have same number of moles of NO and NO2 in our final product, which the student produces by using the reaction represented above. So for every 2 NOs, they can get 2 NO2s by mixing with oxygen. The particle level representation of the equimolar mixture of NO and NO2 in the flask at the completion of the reaction between NO and O2 is shown below in the box on the right. In the box below on the left, draw the particle representation of the reactant molecules of NO and O2 that would yield the product mixture shown in the box on the right. In your drawing, represent oxygen atoms and nitrogen atoms as they are shown here. Well, this is really not a difficult problem, and I think that throws some of the students because they think it's supposed to be something really theoretical. This is a counting kind of a problem. So we're saying, well, I have 1, 2, 3, 4, 5, 6, 7, 8. Over here I have 8 of these little nitrogen atoms, like that. And all of them came from NOs, so that means I must have started then with 8 molecules over here of NO. So I'm going to go ahead and draw those. 3, 4, 5, 6, 7. I'm trying to draw them a little bit random, but not that important. And so I've already drawn 8 oxygens. But over here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 oxygens. I've drawn 8. That means I need 4 more, and they're going to show up as oxygen molecules. And let me draw those so they're together. Alrighty, and that is my answer. Okay, this was worth 2 points, and 1 point was just for drawing only molecules of NO and O2. So if you had just the correct molecules over here, the correct type of molecules, you were good. If you had anything new or had separate oxygens or things like that, you lost that point. And then the other one was for getting all the count correctly, the atoms being conserved. So you should end up with 8 molecules of NO and 2 molecules of O2, and that was a 2-point problem. Now remember to let kids know that, the first part of a question usually is pretty accessible, pretty easy kind of stuff. And this was really nice problem. The part B here, the kid looks up, some of the information and finds the delta H, delta S, and the delta G for this reaction. And this is the reaction of, the equimolar stuff turning into N2O3. And they ask you here to calculate the value of the equilibrium constant for this reaction at 298 degrees Kelvin. So, okay, how can I get an equilibrium constant? Hopefully, the students have learned that there is a equation that relates these two, and the equation is that the delta G is equal to negative RT ln of K, and that K is the equilibrium constant. So our first job then is to go back and let's solve for K. So I'm going to say the natural log of K is equal to, let me clean that up. Natural log of K is equal to, delta G divided by negative R and T. Now before I go on too much farther, I'm going to figure out what R am I going to use. And if we look at, we're talking about energies, so there is a value of R on the exam that's 8.31 joules per mole Kelvin. Okay, so 8.31 joules per mole Kelvin, and that's the one I'm going to use. So I'm going to have things in joules, but my delta G that I'm going to use is in kilojoules, so I'm going to have to change that one. So a kilojoule is equal to 1,000 joules. So the number I'm actually going to use is not 0.87, I'm going to use 870 joules per mole of reaction. So keep that in mind. Okay, let's go back and work on this. ln of k is equal to this, so that's going to be negative, okay, my delta G is 870 kilojoules moles to the minus 1 over, okay, R, which is 8.314, okay, joules moles to the minus 1, kelvins to the minus 1, and temperature, which is 298 Kelvin. So kelvins drop out, my moles drop out. That was wrong, that was not kilojoules, that's joules. Okay, and my joules drop out, and that's good. All of my things drop out because the equilibrium constant, does not have any units. So when I get this calculated, okay, I'm going to find out that my ln of k, okay, equals this number, which I calculate as negative 0.35115. Too many significant figures, that's fine. Okay, now if I want to get k by itself, I have to take e to the ln of k. Okay, that's going to equal k. And I need to have e to the negative 0.35115. And that means this comes out to be 0.70. So this is not a difficult problem, just using this equation, but there are places to be careful. Okay, watch the units and choose the correct value of R, and don't lose that negative sign in there somewhere. That makes a big difference. So the answer is 0.70. This is a 1-point problem, just for getting that value of K. Next, we have to go back, and the question says, if both the partial pressure of NO and NO2 in the vessel are initially at 1 atmosphere, will the partial pressure of the product, N2O3, be 1 atmosphere? And so we could look at this and say, well, okay, here, if I started with, I'd make a little ice box here just to kind of help me organize my information. So if this is 1 atmosphere, and this is 1 atmosphere, and this is, 0, because I haven't got any yet. If I want this to be 1 atmosphere, that means this would have to go up by 1, this goes down by 1, this goes down by 1. So this is possible if the reaction is going all the way to completion, okay? But, it's an equilibrium, and that's a pretty, that's kind of almost kind of around 1. So we're going to have significant amounts of our reactants and products when we reach equilibrium. So the answer to this is no. Okay, the pressure will not equal 1 atmosphere. And you can say that you're only going to get 1 atmosphere if it goes to completion, and it's not because it's an equilibrium. Or you can say something about this equilibrium constant tells us we're going to have both reactants and products, so we're not going to have 1 atmosphere. Okay, so that's 1 point for the correct answer, say no, with a valid justification. Okay, the next part, C. The student hypothesizes that increasing the temperature will increase the amount of N2O3 in the equilibrium mixture. So we're talking about this guy. And the clue here is that back in the chart, it said that the delta H is negative 40.4 kilojoules per mole of reaction. So that means it would show up here as on the product side. Okay, it's going to be an exothermic reaction. So if we were to increase the temperature, then we'd say there's too much heat. Okay, we would expect this to shift back this way, and the NO2 would not be increased, and N2O3 would not be increasing, it would actually be decreasing. Okay, so the answer here is that we disagree. And we'd say, how come? Okay, because this guy is exothermic based on the delta H. And because it's exothermic, when we increase the temperature, it's going to shift toward the reactants, which means the N2O3 is going to go down, not up, and that's why we disagree. If we give a right answer and a good justification for that, we just earned another point. Okay, the next section of this is saying the N2O3 reacts with water to form nitrous acid, HNO2. a compound involved in the production of acid rain, not important for this question. The reaction is represented below. Now the skeletal structure of HNO2 molecule is shown in the box. Complete the Lewis electron dot diagram of the HNO2 molecule in the box, including any lone pairs of electrons. So let's just kind of practice over here. So if I had H, O, N, and O, whenever I do a problem like this, I just go ahead and give everybody an octet of electrons as my starting point, and then I start counting. So if I have HNO2, then I have 1 for hydrogen, 6 for oxygen, 5 for nitrogen, and another 6 for oxygen. So that's 12, 13, 14, 15, 16, 17, 18. I have 18 electrons that I'm going to have in my final structure. But I've drawn 2, 4, 6, 8, 10, 12, 14, 16, 18. I've drawn 20. So I need to get rid of 2 electrons. And what I'm going to do to save those electrons is I'm going to take away this lone pair and take away this lone pair, because they only count for the atoms they're on. And I'm going to replace it with a shared pair, okay, between those 2 atoms. So I still have octets, and I've got 18 electrons now. So here's my picture. So I'm going to go ahead and fill it in the box. So those are single bonds. There's a lone pair on the nitrogen, and I have a double bond. That was terrible looking. Okay, double bond there, and 2 lone pairs on this oxygen. So this would be my picture, and it turns out that is a good picture, and it would get a 1 point. Now, I made a double bond here, taking away lone pair. I could have taken away this one and put a lone pair here, and I would have a slightly different picture. It's actually not correct, but you would have gotten credit because you have to go back now and say, well, how can you tell which of these is the correct structure? You would do formal charge, and that's really beyond this question. So given a valid structure here, we're going to get 1 point for the Lewis dot structure. Now, based on this diagram, okay, identify the hybridization that's involved. Okay, so on this nitrogen, I have 2 bonded atoms. I have 1 lone pair, so we call that a steric number of 3, and so we know that this is going to be sp2 hybridization. sp2 hybridization. Now, based on whatever picture you happen to have in this section, then this answer has to be consistent. So if you drew, I think a lot of students drew something like this, okay, which is not correct. But if they did, and then they said, okay, nitrogen's got 2 bonded atoms, no lone pairs, and they called that sp, then they would have gotten credit, not for this one, but they would have gotten credit for their answer in II. So anyway, the idea is here's the correct structure, and there's the hybridization. To produce an aqueous solution of nitrous acid, the student bubbles N2O3 into distilled water. Assume that the reaction goes to completion and that HNO2 is the only species produced. To determine the concentration of HNO2 in the resulting solution, the student titrates 100 milliliters of the sample with 0.1 molar KOH, and here's a neutralization reaction. Okay, HNO2, the OH because the potassium spectator, and we're going to get NO2 minus and H2O. So here we get this titration curve showing the change in pH. Okay, and we can kind of see from this picture here that here's where the neutralization is happening. There's the equivalence point. So it's 20 milliliters of the base that we had to use. So use the titration curve and the information to determine the initial concentration of HNO2. Okay, so we could do this if we knew the moles divided by the volume. So we can get the moles of our acid because it's going to be the same as the moles of our base. And so let's just take some space down here. So we had 20 milliliters, so 0.020 liters of our KOH times its concentration. Oops. And so the concentration was a 0.100 molar. Of our KOH. And we know that for every 1 mole of KOH, we needed to have 1 mole of our HNO2. So we're done here. So liters cancel out. moles of KOH cancel out, so we're going to have our HNO2, and so 0.02 times 0.1, then we can see that that's going to be 0.001, not 0.002, excuse me. And that's HNO2. Now, what are we talking about? We are talking about the solution, and the solution originally had 100 milliliters, so 0.1 liters. So this, we figured out how many moles of HNO2 to get our molarity. Then we're going to divide by 0.1 liters. So we're going to get 0.00, I said that wrong, 0.02 molar. So I determined the number of moles of KOH, which is the same as the moles of HNO2, because it's a one-to-one reaction, and then I divided by the volume of the acid so I could get my concentration. So this is worth 1 point to get to that answer. Now, some students went ahead and used the dilution formula, which is the volume times the molarity is equal to the volume times the molarity. So not totally appropriate, but it works in this case, and you got credit for it, because it is a one-to-one reaction between the acid and the base. So that formula would give you the correct answer. So the volume of the acid times molarity of the acid equals volume of the base times molarity of the base, because volume times molarity gives you moles, and you have equal moles of acid and base. If it was a 2-to-1 or something, it would have not worked out well. Okay, the next thing it says, estimate the value of the kPa for HNO2. Now, here's our reaction. We're talking about acid, okay, and the acid is HNO2, and it's in equilibrium, with H plus and NO2 minus. So we could write a Ka expression for this, and that would be H plus times NO2 minus all over HNO2. And what we know is that there is a special place, and it's halfway to the equivalence point right here, and you can call that the half equivalence. And what's important about that place right there is at that point, when you're titrating, you are changing this HNO2 into NO2 minus. So if you get to this point, you have changed all of your HNO2 into NO2 minus at 20 milliliters, but halfway you've changed half of it into half of the NO2 has changed into NO2 minus. So at this point, this number and this number are equal to each other, and if they're equal to each other, then the H plus equals the Ka. So if you take the negative log of that, the pH is equal to the pKa. So this special place right here, if you take the pH of the solution halfway to the equivalence point, that is going to tell you the pKa of the acid. It doesn't matter what you started with, it's just when you get halfway there, that'll be the pH equals the pKa of the weak acid. So if we look at this, we see that this is 3 right here, and it's a little bit more, so we're going to say it's about 3.4. Okay, and if we got that, that is 1 point, just for getting the right number there. So estimate the pKa for the acid. Okay, 3.4 is the answer, and we just earned ourselves another point. Now, during the titration, the volume, after a volume of 15 milliliters of the KOH has been added, which species do we have more of? Okay, so what's going on as we go, we are taking our HNO2 and changing it into NO2 minus. At this point, we were 50-50 on those two, so now it says, well, what about we get here? Well, if we get here, then we have changed more of our HNO2 into our NO2 minus. So we're going to have more NO2 minus. So, which is present in higher concentration? Okay, the HNO2 or the NO2 minus, and our answer is for F. Okay, there's going to be more NO2 minus, would be greater than the HNO2 concentration. And we can say because we are beyond the half titration point, and at the half titration point these were equal to each other, and we continue to change HNO2s into NO2 minuses, so we're going to have more of the NO2 minuses at 15 milliliters. Now when we get to 20 milliliters, then we have all NO2 minuses, but that's not this question. And that is the entire question number 2. 10 points.